Okay, so I'd like to thank you all for coming today. So today we have Professor Phillips from University of Illinois Urbana-Champaign giving a talk at Quantum Fluids and Isolation Seminar. So Professor Phillips got his undergraduate degree from Walla Walla College in Washington in 1979. He got his PhD in 1982 from the University of Washington. And then he postdoc at the University of California, Berkeley. And after that, he moved to the MIT faculty from 1984 to 1993, after which he moved to the University of Illinois Urbana-Champaign, where he remains today. So he's gotten many prizes over the years, including the Boucher Prize at APS in 2000. He got the NSF American Competitiveness and Innovation Fellow from 2009 to 2011, and he was a fellow of the American Association for Advancement of Science in 2012. And he's been author of many numerous works on superconductivity and unparticle physics. And today, I'll be talking about superconductivity and Mottness exact results. So please help me in welcoming, either by unmuting yourselves or by virtually clapping your hands, Professor Phillips.
Okay, thank you very much. I was reluctant to give a talk over Zoom because I have had to teach an 800-person class over Zoom, and it's been an absolute disaster. So, but here I go. I've not trusted my better judgment, so we'll just have to see how this goes. So I am putting together two things which I never thought I would ever describe with exact results. So I want to tell you about a model we've solved recently, which allows us to treat Mottness and superconductivity exactly. This work will appear soon in Nature Physics, and my collaborators are my student, Luttinger, and a very talented postdoc, both of them extremely talented, Edwin Huang, who just joined in September. And so this is what I'm going to tell you about. Let's start at the beginning. The beginning, of course, is superconductivity. And this problem took about 50 years to be solved. And it started with the instability that Cooper pointed out. Namely, that if you start with two electrons outside the Fermi surface, they form a bound pair right below the Fermi surface. And it's an essential singularity. The binding energy goes as e to the 1 over the coupling constant. And this was the starting point for understanding, for formulating the BCS theory. In modern language, we understand what BCS theory is all about and why it has been so successful. If we just compute the beta function for an interaction involving electrons on opposite sides of the Fermi surface, the beta function goes as g squared. And this is the only instability of a Fermi surface. I mean, there are other kinds of things that are, finite momentum, et cetera, but this is the principal instability. So we can understand then that if you just ignore all the short-range repulsions between electrons, you aren't throwing anything away. The crucial thing is when the interaction is negative and you're on opposite sides of the Fermi surface. So then we understand BCS theory in the context of Fermi liquid theory. Now, for the cuprates, the problem is very different. We don't start with the Fermi liquid. We don't start with well-defined quasiparticles. We start with an insulator. And from this insulator, when it's doped, we end up with superconductivity. Now, even the starting point for the cuprates is puzzlesome because the Mott insulating state is one which is very particular. It in fact asks you to think about an insulating state in a partially filled band without changing the size of the Brillouin zone. It's very easy to come up with an insulating state if half the K states are unoccupied simply by shrinking the Brillouin zone. And then you only have to worry about the part where you have electrons. But that's not what Mott had in mind. And it's that sort of conceptual problem that has led to the Mott problem sticking around. Now, perhaps in Mott's mind, this wasn't such of a problem because there's a simple way of thinking about a Mott insulator. Let's just think about a Mott insulator in terms of the two forces of nature which are very prevalent. So let's just consider gravity, which is a very weak force, and electromagnetism. And electromagnetism is a very strong force. So if in fact the repulsion between the charges is bigger than some critical value, you won't have infall into below the horizon. And if you do in fact have a certain critical value of the charge for which, and you get below that, you can have infall. And once you have this, you will have a Mott insulator without breaking any symmetries. And in holography, this is now a standard way of thinking about these sorts of insulating states. Charges below the horizon, they don't contribute at all to anything that can carry any current. And so perhaps this was what Mott had in mind. It's unlikely, but you can never sell anyone as smart as Mott was short. So, but the real problem is you want to think about a gap with no symmetry breaking. And the standard model you want to solve in this context is the Hubbard model. So, and once you solve the Hubbard model, you then have to demonstrate that there is a Cooper instability. And so what is the progress? What progress has been made so far on this problem? Starting from the Hubbard type models, Cooper instabilities, et cetera, et cetera. Well, there's been lots of progress on DMFT. There's been lots of progress, quantum Monte Carlo simulations, and of course, any problem in which there's so much at stake, there have been many disputes. Now, I'm going to focus on one of the disputes which shaped my thinking about this problem, because it shaped my thinking as to what the problem was immensely. And David Campbell knows this is one of the things I started working on at Illinois. Okay, so the debate goes back to a paper written by Bob Laughlin and the response written by Phil Anderson. And the paper by Laughlin says that we shouldn't use any of this Mott terminology because we have no idea what a lower and upper Hubbard band is. Nowhere can we find precise definitions of Mott insulator and terminology. The upper and lower Hubbard bands, for example, are vague analogs. And so he said, forget about Mott insulators. You shouldn't even think about the problem. We can't even define any of the excitations that are inherently involved, and hence it's just all vague. And this was followed by a critique of two metals by Phil Anderson and Bhaskaran, and his statement was, 10 years of, he said this statement would be ludicrous if it weren't so influential. And then he says, it is a tragedy of Mott that although he almost certainly won his Nobel Prize for the Mott insulator, Slater, who couldn't think clearly about finite temperature, won the publicity battle. Okay, so what he means by that is, as a result of this paper, there had already been this feeling that it was just easier to think about spin density waves or things that have to do with symmetry breaking. And but that's really not what Mott was talking about, and there's a deep reason for that. He didn't really say what it was. Okay, so back in 1997, I asked the question, what really is the difference between Phil Anderson and Bob Laughlin? And my answer is that it's Mottness. And I then set out to quantify what Mottness was. And Mottness really is about zeros. And the true difference between them is, in fact, determined by one quantity. In all of the stuff Laughlin was talking about, the determinant of the real part of the green function at zero energy is in fact not equal to zero, whereas in fact in Anderson's way of thinking about the problem, it in fact is equal to zero. And this involves, as you'll see, UV ion mixing, which is central to understanding at a deep level what Mott physics is about. Okay, so let's just start by a very simple exercise. Let's just start by counting particles. It's very easy to count particles. You just count them. Okay, now is there a more efficient way of counting? Well, there is. There's Luttinger's theorem. And Luttinger's theorem is a way of counting particles. It's enumerating things that contribute to the density, to the charge density in the system. So here, what Luttinger tells us is we take it's just the Heaviside step functions. We're evaluating the real part of the green function at zero frequency. And we're looking for the part which this thing is positive. So in fact, what we're doing is integrating in some contour in momentum space where the real part of the green function is positive. Okay, so there are several ways a green function can become positive. It can become positive by going through a pole, in which case, every time you encounter a pole, which is the signature of a particle, it makes sense that you should count that. So it makes sense then that this also is, this puts some sort of physical interpretation to this formula. But there's another way in which a function can become positive. It doesn't have to have this singularity here. It can just cross the positive axis. It just cross the x-axis and become positive. This is an example of a zero. And in the original formulation of this theorem, zero crossings and poles contribute equally. Okay, so what are zeros? Here's what a zero is. If you look at the imaginary part of the green function, which gives you the spectral function, this is entirely a positive quantity. Now, because of the Kramer-Schrödinger relation, since this is a causal function, one can construct the real part of the green function. And you just go and do this integral. And I don't have an omega minus omega prime here because I only want to get this at zero energy. Okay? Now I have a positive thing over some variable that can go from minus infinity to infinity. Hello? Okay, and as a result of this, this integrand can in fact become positive and negative. It's entirely because of the frequency dependence. So this is a weighted moment of the spectral function. So you have some stuff below and above the gap. These things can in fact have different signs. If they have different signs, it's entirely possible that the real part of the green function can in fact become zero. And the important thing here is that this is within one band. If you have a symmetry breaking that goes on, you can never, the full green function, it splits into two bands. Each one has a resolvent, but the product of them will never be zero. The important thing here is you have this structure within one band. Okay, so the determinant of the real part of the green function, single band is equal to zero. So it's telling you about a gapped structure. Now, why did this come into Luttinger's theorem? It came to Luttinger's theorem because Luttinger reduced everything down to a quantity which looks like this. It's a logarithm of something. And the singularities of the logarithm are two places. Is the only function that does that. Either when the argument is zero or the argument is infinity.
Like COVID.
Is there a question? Okay. Right. And so as a result of this, zeros are on the same logical footing as the thing we associate with counting particles. And hence, as far as Luttinger is concerned, what we're supposed to do is look at all of the possible ways this quantity can change sign. Okay, and hence that's the nature of this statement. Okay, now are zeros important? We know that poles are important. There's a physical consequence when the chemical potential passes through a pole. It's an excitation which contributes to all of the physics. What about zeros? Okay, now, when you dope a Mott insulator experimentally, at least in the cuprates, what seems to form are Fermi arcs. And by a Fermi arc, I just mean a region of excitations where you have pole-like excitations that don't go all the way to the edge of the Brillouin zone. So an extreme case of this would just be a dot, okay, a nodal metal, as it were. Whether it's a nodal metal or this, it doesn't matter. On either side of this, the real part of the green function changes sign, because really this is a set of pole-like singularities here and here and there. Okay, so we have this going from negative to positive. Now consider a path in this Brillouin zone that goes here and comes back around here, but doesn't cross this region where you have a mandated way of changing the sign of the green function. If you come back along here, how can you change the sign of the green function? The only way that you can is if there is some mechanism between here and here that changes the sign. And the only way to do that is if, in fact, you had a zero. Another way of doing it is if you had another quasi-particle band here, in which case you go from negative to positive back to negative, and there's no problem in getting the right sign. So the important thing is that if in fact you do have an arc and it's not a closed surface back here, you have to have zeros, and the zeros have to be here or there. Okay. Okay, so Fermi arcs are a very strong indication that in fact zeros are important in the Mott problem. And here's what the experiment actually looks like. This is underdoped, I forgot which material, but as you see, it's well known, you do end up with these Fermi arcs. Okay, now, so the problem then is, that makes the cuprate problem different from the Fermi liquid problem or the lead problem, is that you have to somehow come up with a way of understanding the Cooper instability in the presence of this zero surface, or both zeros and poles, since undoubtedly if you have a Fermi arc, you have zeros and poles. So you have to come up with a way of understanding how do you formulate the problem of a Cooper instability in the presence of a Luttinger surface in general. Okay, so there's been a paper recently which certainly motivated us, and this is a former postdoc who wrote a paper considering just the case of a zero surface, and these things are fairly well separated. And his conclusion is that pair fluctuations on top of such a thing leads to SYK physics. And what we were interested in is there a model that you can solve completely exactly to see if this sort of thing is true? Okay, so let's look at the simplest model that has zeros. The simplest model that has zeros is one that has absolutely zero physical content. It's the atomic limit of the Hubbard model. But I just want to be systematic so that everyone is with me when I finally go and write down the model I want to go and solve. So it's just this model. There's no kinetic energy, okay? And these two terms commute. The green function for this model is well known. X is just the deviation from half filling. Here is the two-pole structure. And this two-pole structure gives rise to a zero surface. At x equals 0, this term and this term identically add to give 0 if you set the chemical potential equal to 0. Okay? Now, if I were to apply Luttinger's sum rule to this, what would I get? I would obtain that n is 2 theta of this quantity. Okay? Just by combining both of these terms. Okay? And as this advertises, if in fact this is equal to 0, this means that if I set the chemical potential equal to 0, what I will obtain is that this formula will reduce to 1 because I have theta of 0, which is 1/2. 1/2 times 2 is 1. I obtain the filling is equal to 1, which is correct. Okay? However, if I have a single site and I have these two bands here, I can put the chemical potential anywhere between, let's say the lower one is at minus U over 2, the upper one is at U over 2. I can put the chemical potential anywhere in between here. It's no longer fixed because the system is an insulator. And hence, if I choose it to be slightly above 0, this quantity, how do I move? Oh, there, okay, good. Okay, yeah, the chemical potential, if it's slightly positive, n will be equal to 2. And if in fact the chemical, sorry, what did I do? Somehow I did something that is, I was trying to get to the point where the Zoom things were not showing up on my screen. Okay, is everyone still there?
Yeah.
Okay, okay, good. Okay, so sorry. Yes. Okay, so if
we can't see your screen now.
Oh, sorry, I'm not sharing the screen. I'm not sharing the screen. Sorry. I'm not sharing the screen. Okay. Okay, now you are sharing the screen. And okay, is everything fine?
Yes, perfect.
Okay, good. Okay, so let's just review this. The chemical potential is not uniquely defined, or at least you have some freedom. Now, there might be some other rule that you might think about, but at least when you have a gap, you can put the chemical potential anywhere in the gap. And remember now, zeros come from a balancing of the spectral weight above and below the gap. And so there's this moment that you are computing, and you can change the balance between the upper and the lower bands simply by changing where you put the chemical potential. Okay, so consider the fact that the case in which mu is positive, but less than U over 2, in which case this is negative. This down here is also negative because this is less than this. This is positive, and hence you just end up with 2. And in the case where mu is now negative, this is negative. Well, this can never be valid, and in fact, you end up with n equals 0 because there's no solution. So my point now is that this is a rather curious thing. Zeros have no physical content, at least when the chemical potential crosses a 0, it doesn't mean you're counting a particle. So what it does is it offers a possibility for separating the Luttinger count from the actual number of particles. Okay, and here's a simple illustration of that. Now, it might be that the real principle that they should say should dictate where you put the chemical potential is that you should use the chemical potential that is determined by T equals 0. And for this simple problem, that would give you unique when mu equals 0. And the sort of subsidiary reason is that that's the point at which you get particle hole symmetry. Okay, so let's just say that particle hole symmetry should go and dictate this, okay? Now, what I want to show is that there are cases in which that doesn't always work, and such is going to be the model that I present. Okay, now, so this is an exactly solvable model with zeros. It has no physical content, but it does sort of illustrate a deep problem. Okay, now can the same physics be retained in the presence of the kinetic energy? Okay, so the kinetic energy term we want is just the standard one, okay? Now in 1992, Hatsugai-Khomoto wrote down a model which is exactly solvable. And I think by 1993, everyone had forgotten about this model. Okay, the potential term that they added is not the Hubbard one. The potential term they added is one in which you have an all-to-all interaction, but it preserves the center of mass. So every term is connected that satisfies this constraint. Now, why did they introduce this constraint? I think they did it by reverse engineering. For those of you who can do a Fourier transform in your head, so you simply rewrite the problem in momentum space. Subject to this constraint, you know exactly what you're going to end up with. You're going to end up with a problem that looks diagonal in momentum space. Okay. And if it's diagonal in momentum space, although this is a quartic term, it should be a solvable model. Okay? Okay, so now the key thing here is if this interaction term looks like this, and the kinetic term also just depends on the same operators, these two terms commute. Now you think nothing interesting can happen in a model in which the kinetic and the potential terms commute. Not so. Okay, the key thing about the HK model is that it represents a class of models in which absolutely this is true, but you don't have to have the same momentum here. Okay, so it's the general class of terms in which, subject to this constraint, you can have any number of terms here, but it has to be such that you don't destroy the commutativity. So all you can have here is density. Okay. Now we know this is a problem that is solvable. The exact green function for this problem looks like this. Okay, and the lower and upper Hubbard bands are indicated right here, and they don't represent simple excitations. For example, consider that you're at a certain value of momentum of when this quantity is in fact equal to 1. In which case, this is going to go away, and all you have is just the upper band. Or consider a case in which this is equal to 0. You only have this term. To get zeros, you need both of these terms. This represents the lower band, and this represents the upper band. So whatever the excitations are, that are present here, they're not single electron excitations. They're composite excitations. And they correspond to these operators right here. And for the HK model, these operators completely diagonalize the green function. So there is no cross-mixing between this term and this term. Unlike the Hubbard model, in which case, of course, there is dynamical mixing between this and this. And that's why writing down Hubbard operators is sort of a non-starter, because you have no control over anything. But in this problem, those are the natural operators that make the problem solvable. So the spectral function only has diagonal contributions from this and from this. Okay, so let's look at the green function. The green function looks exactly like it did in the atomic limit. It's just now I have a kinetic energy, because it's the same structure in momentum space that is now just gets mapped onto whatever I had in real space for the atomic limit. And look at the form of this term. It's not morally correct to call it a self energy, but let me just use the same symbol anyway, because I haven't gone and done any perturbation theory. It is the term in the green function that comes from just summing up these two poles together. And look at this term. This term diverges both in the real part and the imaginary part. So, which means now the green function, if both the real and imaginary parts diverge, you in fact have zeros. And if you do, this means there is no Fermi liquid quasiparticle anywhere in the system. And we have the exact green function for it. Okay, now I have these two bands. Their width is determined by the spreading of the kinetic energy. So let's define delta E as U minus 4 dt, and this quantity I'm going to call W. Okay, so that's W. This is what the spectrum looks like if you sit at half filling. Okay, half filling. U is bigger than W. The bands are well separated. They're well separated. Only this one lies below the chemical potential, which means the occupancy here is 1/2. The occupancy up here is also, well, it's 1/2 as well. But both of them contribute, and that's why you get the zero surface that sits between. Okay, so this is the upper band and the lower band. It describes an insulator. Okay, and this is where the Luttinger surface is. Anytime you change the size of the Luttinger surface compared to this, what has to happen is that the occupancies have to change from being 1/2 to either 1 or 0. So right now, in this case, there is no double occupancy. There's a gap to creating double occupancy, and that's what this indicates. Okay? Unlike the Hubbard model, there is double occupancy even in the insulating state. There is no such thing here in this model, because there's a clean separation between the upper and the lower bands. There's no dynamical mixing between them. Okay, now let's stick at n equal 1 and decrease u. Well, what we're doing now is making it possible for you to have double occupancy. And there are 3 distinct regions here now. At any time you increase the probability of having double occupancy, you change the size of the Luttinger surface. Okay, this is the corresponding Luttinger surface here. The first thing I want you to know is that it doesn't occur anywhere we have double occupancy. It can't. The Luttinger surface is a balancing between spectral weight in the upper and lower bands, where the occupancy between these is the same. So it has to blanket wherever you have. So here are the occupancies. This is 1. You have upspins and you have downspins. This part, you only have one of these bands occupied, namely the one below the chemical potential. And here you have no occupancy at all. Right. Okay, crap, what happened there? Okay, let me stop touching my computer. It seems to be jittery. Okay, so this region, double occupancy. This region, single occupancy. Here you have no occupancy at all. This is the unoccupied part of the lower band, unoccupied part of the upper band. So this structure is what you should have in mind when we think about the complication that comes from this model. Okay, now this is U less than W, we have a metal here, okay? Now there's another way of getting a metal. Now, before I go on to that, let me just point out something. The occupancy here is 1/2, which means that only one of the spins, which means that we don't have any double occupancy in this region of K-space, but because of SU2 invariance, we have to have all possible combinations of the spins. So in fact, the metal is hugely degenerate, and you can write down the wave function for the metal in this region of K-space simply by, we have a doubly occupied part, we have, this is just one particular state, but we have to have all possible combinations of the spins that in the singly occupied part such that the total wave function is SU2 invariant. Okay, and that's why this is a very strange situation. It's a hugely degenerate metal. Okay, now consider the case in which you had the Mott insulator, but now you doped it, n less than 1. Okay, so these Luttinger surfaces are not, well, it's here, but this only, the Luttinger surface always only covers the region of the spectrum where you have single occupancy. Because then both poles are contributing, and you end up with a 0 as a result of the balancing of the spectral weight above and below. Here, there's nothing to balance, and hence there can never be a 0. Okay? Okay. Now, with this in mind, we can compute the Luttinger sum rule. And here's what the phase diagram looks like for this system. Here's U over W. If we look on this line here, x equals 0, here we have the metal. This is the non-interacting point. Here we have the Mott insulator. And A corresponds to the first figure I showed you. And that one, the Luttinger sum rule, completely satisfied. This being 1 tells you that the Luttinger sum rule relative to x, this is looking at the ratio of the two. So equal to 1 means there's no problem. The Luttinger sum rule is identically equal to the filling in the system. Anytime you get a deviation from this light color here, you see in general that the system is, has no correspondence between counting the sign changes of the green function and the physical charge density. And so in general, you see the system is a non-Fermi liquid. Okay, and we know exactly what the Luttinger count is, and it deviates from the actual physical doping level. Okay, this one corresponds to some point over here, in which case the occupancy is closer to 2, but it should really be 1. Okay, so in a previous paper, what we'd done is we'd computed a signature of this insulator metal transition by looking at the two-site entropy and the thermodynamic entropy in the system. And as we can see, right when U is equal to W, you really do have a change in the entropic content of the system. And in fact, you see that it's a fairly good signature in both this local quantity and the more the thermodynamic quantity, that in fact, you really do have a change from a metal to an insulator. And all of this is completely computable exactly. And so our starting point then is this HK model But before I go on, let me just tell you what the HK model leaves out. Okay, now in the Hubbard model, the mechanism of the gap and the dynamical mixing between the Hubbard operators is mixed. And by that I mean the following. In the Hubbard model, if you just start off with one empty site, because the kinetic and the potential terms don't commute, you will generate more empty sites, because no eigenstate of the Hubbard operator is an eigenstate of local occupation. So these red and blue things are double occupancies. So you have dynamically generated empty sites, which means since these are empty, it's changing the spectral weight at low energy in lieu of something that happened at higher energy. This dynamical spectral wave transfer is not present in the HK model, because this commutator is equal to 0 in the HK model. Okay, now I will come back to this at the end. I just wanted to be clear what this leaves out. You can still get the gap. You still have all of this Mottness and zeros, but you don't have spectral wave transfer, which is the T over U correction to everything I'm talking about. So that's sort of the surprise here, that you have non-trivial physics and you can separate these T over U corrections from the U physics. Okay, now that we have this exactly solvable model, this HK model, we can ask the question, as BCS did, what happens if we turn on an interaction term, a pairing term? Okay, does that lead to an instability? Is there a pair binding? Okay, now formulating this problem is very simple. The pair binding energy is just, you take this Hamiltonian here, you compute the expectation value with two different ground states. One is the initial ground state I had of HK, and then one is this one here, which is the ground state of this system, and you ask the question, which one is the true, which one is a more accurate description of the system? If this in fact is lower in energy than this, you're looking for, in fact, this quantity to be positive. Okay, so it's a very simple problem that you need to go and solve. You can go and solve it exactly. This is the condition for the pair binding constraint in the HK model. And you're summing here over the part of the region in K space where you have, where the occupancy is 0, which means these things are 0. You can easily go and do this integral. And here's what you end up with. There is a non-zero binding energy. This is the exact, well, it's not, it's in the limit U is, I mean, W is approximately U. Okay, so here's the form of the answer. And this is the exact numerical answer. And you get a pair binding energy. Okay, so this is the exact Cooper instability in a system that gives you a Mott insulator. Okay. Now, if we have a system that we can do these kinds of calculations exactly for, a better indication of some sort of superconducting instability in the ground state is in fact the pair susceptibility. Okay, so let's go and calculate the pair susceptibility. In fact, we can get that exactly as well. Because of the form of this Hamiltonian, things are certain quantities are very easy to go and compute. And in fact, all of these sums in here are very simple. And you can show that the full susceptibility is just the susceptibility in the absence of this pairing interaction. And it looks, I mean, divided by 1 minus g times chi 0. Okay? And the chi 0 is just this quantity which we can go and calculate. Okay, So chi0 is just this integral that you have to go and do. The density of states is this quantity which has these weights for the upper and lower bands. And you can solve this for TC. See, TC is just a solution to this. And here's what it looks like. Okay, there's the essential singularity, and here's this prefactor here, which is W4/4/5, and this is just the width of the band. Okay, good. Now, so that's all exact. Everything I've told you so far is completely exact. We know everything about the system before we turn on the pairing interaction. We know that the system has a superconducting ground state. So now the question is, can we go and characterize the superconducting state? We know the ground state, we need to know what are its excitations. So the best way to do that is to make an ansatz for what the variational wave function for this system looks like. And Edwin wrote down the wave function that I want to tell you about and some of the consequences of this wave function. So this is what the BCS wave function looks like. Now, let me just make a trivial rewriting of this wave function. So I'm only taking the product over positive momenta. If I take the product over positive momenta, I need to put back in the minus momenta part. So it looks like this. Okay, so this is squared and this looks like this. There are three terms here. Now, why did I do this? The reason I did this is I need to have three different parts to my wave function to describe the HK model. I need a doubly occupied part, at least when it's doped, a doubly occupied part, a singly occupied part, and an empty part. This is doubly occupied, empty, this is singly, which means to be able to describe the range of physics in the HK model, I need to have three variational parameters, not just two. Because it's not a Fermi liquid anymore. Okay, so these are the three parts that I need to describe. Doubly occupied, the singly occupied part, and only in the singly occupied part, it's that range of momenta that have the Luttinger surface, the zero surface, and of course, the empty part. Okay, so the generalization that we used of the BCS wave function is indicated right here. Okay, so we have three variational parameters. And with these, and YK describes the doubly occupied part, BK dagger, B minus K dagger. This is the empty part. And this over here is the singly occupied part. Remember, BK is a composite of CK, C minus K. So only one of the Ks is getting any occupancy by each of these terms acting. Okay. Now, so the variational condition is this is equal to 1. You just vary the energy subject to these constraints. The whole point of doing this is to end up with the gap equation. We end up with something that looks like this. This quantity right here is a generalization for the quasiparticle excitations that's relevant for the excited states. And these are indicated by this, the gap equation. Here's the gap equation, and here it is. You just go and solve this in this limit, delta much smaller than U and W. This is what you end up with. Okay, and we had TC before. Let's go and compare these two things. Here's the gap, here's TC. Let's take the ratio of these things. Now the important thing is, what is in the exponent here and here is not the same. In BCS, they are the same. And as a result, in BCS, this ratio is just a pure number. Here, it's not a pure number. This ratio goes off to infinity. Because in the limit that G goes to 0, the weak coupling limit is what you're interested in, because you're perturbing the HK model with the pairing interaction to see what happens adiabatically as you turn this on. What you're seeing is this ratio is now a very large number. So this is not looking at all like BCS theory. Okay, so this is non-BCS superconductivity. Not a surprise. We didn't start with the Fermi liquid. We started with the Mott insulator. Okay, now if this is not looking like BCS superconductivity, then the fundamental things which give you the excited states should also not look like the Bogoliubov excitations. These are the Bogoliubov excitations. They're linear combinations of the elemental excitations of the Fermi liquid, which are just electron creation and annihilation operators. For our problem, the elementary excitations of the Mott insulator have nothing to do with bare electrons. They're composite excitations having to do with these things that Laughlin thought were ill-defined. But we know exactly what they are. They are the upper and lower Hubbard band composite operators. So that's not going to work. So these new things we call pions. These are our initials in the paper. And here they are. They're linear combinations of the things which give rise to the composite nature of the pole structure in the HK Green function. Now, the way that you know if you have the right answer for the Bogoliubov excitations is that these things should annihilate the BCS ground state, because there should be none of these in the BCS ground state. You can in fact check that. Either of these acting on psi gives you 0. And it gives you a gap in the spectrum can be obtained by going and computing this expectation value. It gives you this extra piece here, and that thing looks exactly like this. And this delta is the thing that we determined earlier. So in fact, that quantity really is the gap, and these are the excitations. So we have a non-BCS superconductor, non-Bogoliubov quasiparticles that come about from the Mottness of the problem, and that's the excited state spectrum. Okay, and it's because, and these are two of these because superconductivity affects both of the bands. Okay, now let's just think about how this is going to happen. In the standard BCS case, you always think about this shadow band here, and you're going to see a gap at these points right here. Well, that's exactly what happens in this case. And this is the pion band, okay? And as you see right here, there's the gap. So this looks a lot like BCS, okay? There's a shadow band up here as well. In this case, in which case it's just the half-filled metal. You have this band, that one, this one, and that one. And so everything is looking just like BCS, but the excitations aren't. Okay, now I'm running out of time, but I had some technical issues. Should I end now or should I go on?
Keep going. I think that's fine.
Okay, it's not like we have a dinner date, right? Okay, so now that I have all of this, we should be able to solve a very concrete problem, which has always bothered me, and everyone knows what this is. And it came from this very famous paper, and it states, it's right in the title, superconductivity-induced transfer of in-plane spectral weight. Now, the key thing of Mottness is zeros, and that means that all energy scales are separate, are connected. You can't just throw away one because you have this zero surface at zero energy. Okay, now what they noticed is this. If they look at the integrated spectral weight, which you can say, let's talk about a low energy part of the spectral weight, 0 to 1 eV, and let's look at the high energy part, 1 eV to 2 eV. In a Fermi liquid, these would really have nothing to do with one another. But what they found is, and what they're trying to do is understand, does a separation of energy scales emerge once superconductivity happens? And what they found is no. What they found is once you go through the superconducting transition, the spectrum at high energies goes down, and the spectrum at lower energies increases. So there's a transfer of weight from the high energy part to the low energy part. Now, to quantify this, you can simply just look at the difference. This change in the spectral weight on the low part versus the spectral weight that was there originally, it's around a 3% increase. And that's sufficient to account for the sort of like, the saving of the Coulomb energy, as it were, the condensation energy inside this strongly coupled superconductor. So it's a 3% effect, okay? And this also shows up. So here's the key answer. It's transferred from outside the infrared range from the UV. It's a blue shift. So this is known as the color change. And this has been known for a long time. And explaining it, you would think if you have started from a non-Fermi liquid that has this Mott physics in it, this should be captured by this. Now, experimentally, how this plays out is that normally, to recover the superfluid density, you would simply integrate to maybe at most 10 times the gap. But in the cuprates, you have to integrate to 100 times the gap. And that's this connection between high and low energy physics. So this sum rule is exhausted at 2 electron volts, okay? Not like 100 millivolts. Okay, so can we describe this? Okay, the answer is yes. So we just simply computed the spectral weight in the lower band as a function of G over the result when G equals 0. And what we found is here. Okay, so this depends on the value of U over T. And the size of this quantity decreases as you increase U over T. Okay, so let's look at a reasonable value of G over T, like here. Okay, this number is, it starts at 1. So we're looking, this thing is bigger than 1, so that's great. This is around exactly where the experiments are. So this increase that we're seeing from 1 up in this direction for reasonable values of the coupling constant is right around where it should be. Okay, why are we getting this effect? Because no one's been able to explain this effect. A hint as to what is going on is that this is decreasing as you increase U over T. Okay? U over T has to do with dynamical spectral weight transfer. Okay? Once you put in this pairing term, these two terms don't commute, which means there will be dynamical mixing between the lower and the upper bands. And remember, that's the one thing the HK model didn't have on its own. In the presence of superconductivity, you have dynamical mixing between the lower bands. And dynamical mixing between the lower bands is well known to increase the weight at lower energy. Okay? So remember this cartoon. You start with one empty site, just turn on T over U corrections, and you always end up with more empty sites than you started with. And this is well known. In fact, it was first shown by Harris and Lang in 1967. So this is just the atomic limit, which is what HK is. In the presence of the pairing term, there's now dynamical mixing between these two. And this correction, it scales as T over U. It's entirely positive, and it just increases the spectral weight here. Okay? So we think this is a very general effect, that this in-plane transfer of spectral weight is coming from, or this color change is coming from the dynamical mixing between high and low energy parts of the spectrum. Okay. Okay, I am going to skip the next 3 transparencies and just go to the last thing, which is the superfluid density. Okay, so I'm now characterizing all the things about the superconducting state. The last thing we were able to compute, and the referee asked for this to make a complete story, is that it's well known that in Mott systems, the superfluid density is suppressed. And the referee said, look, you have all the ingredients. Can you show this? If you can, your paper's in. So we went and computed it, okay? So here goes. This is U over T. This is the Fermi liquid, okay? That's the spectral, this is the superfluid density. Okay, now this is what the superfluid density looks like in the Mott insulator. Oh, sorry, I didn't show this. But this is the audience participation part. What do you think is hidden here? David Campbell, what should be the shape down here?
Not sure, Philip. The boy you said looks like it has structure in it that goes down to zero.
Yeah, that's right. Okay. I know it's about lunchtime. It's the golden arches, okay? That's what it looks like. Okay.
All right.
Okay. It has to look like this because Mott physics takes over here. You can't get a superconductor there. So the real part that's of interest to the cuprates is this region from here to here. And as you see, there's a huge suppression of the spectral, of the superfluid density. Okay, so we produce this, and as I said, the paper will be coming out shortly. But that's the key thing, okay? Because we started with a non-Fermi liquid, because we started with not just a non-Fermi liquid, with a doped Mott insulator, we had all the ingredients to have a mixing between high and low energies. And once you have that, if that model is under control, so will the pair instability, everything else. And this is Mottness induced suppression of the superfluid density. And you should have all the ingredients necessary to start systematically treating the Mott problem. And the nice thing about the HK model is it separates out the Mott gap from dynamical spectral wave transfer. In fact, it's the only model that does that. So since dynamical spectral wave transfer is a T over U correction, what we hope now is that we can develop a kind of Shankar/Polchinski argument that even if we were to add in these dynamical corrections, the physics that I just presented for the last hour or so would still be there. In which case, that's a way of sneaking up on the Hubbard model. Okay, this gives rise to that. We have these new fundamental excitations we call pions. The H, I guess, is silent, although Edwin is anything but silent. And sorry, and I guess that's it.
Okay, so if anyone has any questions, feel free to unmute yourselves.
So, Philip, as you said, this is sort of a concocted model. And you even said it was a toy model. What are the chemists going to say to you when they want to talk about coppers and oxygens and transfer and things like that? How close can you get to something? That's the first part of the question. And the second part is, what's your view of the enormous number of attempts to prove the 2D Hubbard model in some region actually has superconductivity? An honest appraisal of that.
Okay, so the first question, my goal was very modest. After 30 some years, we still don't have any demonstration of a Cooper instability in anything other than a Fermi liquid. So my goal was to come up with an exactly solvable Mott problem that I can illustrate how different all of this is going to be. And the fact that it comes out close to what is in the cuprates is entirely a bonus. So I think there is a lot to be learned by looking at models, because no one would have ever thought that P squared over 2m describes lead, but it does, because there's a theorem. Okay, there's an RG principle that protects the Fermi surface. what I'm trying to establish here is there a similar RG principle that protects Mottness? And the essence of Mottness is these separated bands with zeros. Okay? And insofar as that seems to be the essential part of Mott physics, start with that and see how far you get. Okay, now the Hubbard model. Yes, the Hubbard model seems to be, remember now, my pairing came from taking something outside the HK model. So certainly the HK model left to its own devices isn't going to superconduct. Okay, so
Right.
the question in the Hubbard model is a fairly different question. Does somehow the dynamical mixing terms in the Hubbard model, does that somehow lead to an instability of the Cooper type? The best numerical answers seem to indicate that unless you turn on T prime,
Right.
you're not going to get that. So it's a details question. Whereas the question I was trying to answer is a principle question. You start with a Mott insulator, what do you end up with? Okay, and I hope what I've done is uncloak, or I hope what we have done is uncloak general features the same way that we have cataloged what's in BCS, delta over 2 delta over T ratios, what the heat capacity looks like, Hebel-Slichter peaks, all of that. I mean, these are just models, but they give rise, they describe, what's going on in these systems fairly accurately. If this is the same, so this I'm hoping will serve the same sort of purpose that BCS did, which certainly doesn't have all the details of every simple, every elemental superconductor in it, but it has enough.
So if you put in the ratios that are known of TC over delta for the high TC materials, what does that tell you about your parameters?
Oh, yeah. We have not done that. That's a very good thing. Yes. Yeah, that would be a very good thing to do. In fact, that would give us, control over this color change, which is entirely governed by the ratio of G over T. Yes, that's right. That's something we should do. But the referees were more interested in, can we use this model to exploit, to get at all of the strange stuff that seems to be happening in the cuprates.
Any other questions?
Yeah, I actually have a quick question. Oh, sorry.
I was just going to ask, how is it possible that you don't have particles, but you have a Green's function?
Okay.
I mean, like thinking back to Feynman diagrams, the Green's function represents a particle created and then annihilated at a different location, like a correlation function.
Okay. Right. It's because the operators, it's because underlying this model are composite excitations.
Mm-hmm.
And and these things give rise to this. Okay, your question is essentially Bob Laughlin's question. Okay. Yeah. Where is that? Right here. Yes, good. Let's just play this, okay? This is the exact Green function. C dagger, okay? That's what it is. But you see, this Green function is schizophrenic. It doesn't describe just one pole, it's a sum of two poles. And look at the weight of these things. It depends on the occupancy in K space. Okay? Which means the underlying things here are not In other words, normally when you go and compute a green function, you use operators that have commutation relationships that are just pure numbers, C numbers as they call them.
Okay.
Okay, if you're getting something that depends on the occupancy, it's telling you that when you permute these things, you're getting something that is a new operator.
Okay.
Okay? That's what's going on here. That's the only way to end up with zeros, is if you deviate from the standard elemental creation Fock space, and you go to a space now in which it's inherently interacting. So there is no Feynman diagram you're going to go and write down to give you this, because this is inherently non-perturbative physics. It would be incorrect, for example, to go and write down Feynman diagrams because you don't have a Fock space.
So, okay, so basically because you're getting such a weird case, you're kind of having to extend the idea of Green's function?
No, I'm saying that a green, even, you can always, okay. Whether or not the green function has poles, that's the question you are really asking, is not an indication. The important thing is what else is in the green function. If the green function just has poles, then of course you have a Fermi liquid. This one has poles, okay? But look at the weight of these things. But the thing of it is, as a result of it looking like this, it also has zeros. And if your green function has zeros, then your elementary excitations are not single particles.
So I have a question. This is Bernardo Barbiellini.
Yes.
I have a question because, you know, an important point is also to have a branch point. For instance, if you take another analytical model, will be the Fano-Anderson model. And I think there is some calculation done where they could calculate all the green functions and think, I mean.
Yeah.
And then they see the appearance of branch point.
Yes, that's right.
I was wondering if here you have some kind of branch point which appears.
As far as I can tell, we do not. We strictly have zeros and poles. Okay. Another way of getting a strange green function, yeah, is to pick one that has that represents a Luttinger liquid, something like that. That's not what we're doing. Okay. Because Luttinger liquid green functions, you can't really go and treat the underlying Hamiltonian, you can't really go and treat the instability exactly. So we wanted to make exact statements. So that's why we went and looked at the HK model. And as I said, what we did could have been done in 1992. Because it was just a model that was written down then, but no one did it. Because I think people thought the HK model was a throwaway model.
You mentioned, you made some brief connections to the SYK model.
Right.
Does that, does the connection between the two provide any?
Okay, so nothing, so let me tell you the connection between the two. And this is Shandon Setti's work, this is not our work. Okay, if you have a Luttinger surface only, so you can't dope the system. So in other words, if you're in the insulator, and so you have no red things like these things over here, you have no red regions at all. you just have a Luttinger surface over the whole Brillouin zone, separated upper and lower bands. If you turn on an interaction for the pairing that's on the order of the gap between these two, then apparently that thermodynamic transition looks a lot like SYK physics. Okay, and that's what Chandon-Setti's work establishes. We did not consider that regime. We were interested more in the dope cases because we did not consider it because we were not interested in it, because we were interested in dope Mott insulators. So this is not a generic result. So any relationship of SYK to what we have done or to this general problem of pairing in systems that have Mott physics is not generic to SYK. It's one particular regime, and so we didn't consider it.
I'm not exactly an expert in the SYK model, but my basic understanding is that there's some kind of a infinite range interaction term, just like everything's interacting with everything, but it's for spin, right?
Yeah. Okay. So
that's
okay. So right. So things have a way of all being connected. Okay. So why is it that HK was on my mind? It was because, Subir wrote down that very nice model. It became fashionable. And if you look at this model, well, that's the nature of the interaction term. Okay? These can be, there's no restriction on what J and what these J sub i's are. They can connect sites as far away as you want, just as long as the sum of this and this and this and this are the same. So there's that thing they have in common, but that by itself is not sufficient to make the two models the same. For example, if you look at the green function here, this green function does not have the basic symmetry of the single particle green function in SYK. It doesn't have SL2R symmetry. So at the level of the green function, the Hamiltonians, they're completely different models. Why, when you turn on pairing on the order of that, you end up with something that looks similar? I don't know. That's not a story I am pushing or that we are pushing. That is Chandon-Setti's story, and that's his thing. So I don't understand why there is any deep connection.
So Philip, that term is sort of like a pair hopping term, which takes annihilates things at J2 plus J4 equals J1 plus J3 and moves them. It's almost pair hopping.
Well, it's not exactly. It's just the standard interaction term in the Hubbard model.
What?
It's just the standard interaction term in the Hubbard model.
Yeah, but remember Mottness did this sort of business where he did pair hopping model, and this does hop pairs. It takes a pair at J2 plus J4.
Right, absolutely.
J1 plus J3.
Yeah, that's right. So in fact, any four-body term can always be construed that way. Yeah, any four-body term can be construed that way. Because you can always group the creation operators together and the annihilation operators together. So
I got a question.
I'm not sure.
okay.
Could you assume if these what do you call them? You called them pions?
Pions, yeah.
If these kind of excitations were observable, I mean, could you observe them?
Could you repeat yourself?
Could you observe them in some direct way, or do you have to have kind of indirect?
Right. Okay, that's an excellent question. Bogoliubov excitations, you certainly can observe. For example, tunneling spectra. There's a whole lot of stuff we need to go and work out right now. In fact, that's Luke's thesis. Okay, so Luke is the Cooper of PYH. Edwin is the Schrieffer. He wrote down the wave function. Okay, and I guess that leaves only one person, but I won't say what that means. Anyway, go ahead. Yeah, so we are doing that sort of thing, okay? We're trying to now work out all of the nature of, because once we have, remember, all of the physical stuff that comes into BCS, it's just different combinations of these coherence factors. And so right now we're working out all of that.
Yeah, actually, the question I wanted to ask also, if you can calculate susceptibility and optical.
Yeah. That's one of the things we're working out. We're working out the thermodynamics. If this is sort of a template for what superconductivity looks like in a dope Mott insulator, then we should be able to go and calculate all of those things and match them up.
Right. So you expect to find something like van der Marel.
Yeah, absolutely. Look, we're going for everything here, okay? We aren't playing a small game here. We want to see if this gives rise to the physics of dope Mott insulators. It is a toy model, but so is Fermi liquid theory.
Right. But I'm a little bit, because the fact that you don't find a branch point, I'm a little bit concerned if you can describe this very strange exponent, because at the moment, as was indicated, your green function has only poles, and so it's. I agree that you are.
No. This is just hold on a second here. My green function doesn't just have poles, sir. Okay.
Okay. Then that was my question.
Here it is.
Okay.
So this is why I wanted to make this absolutely clear.
Right. But then when I asked you the question,
is a sum of two poles, but the weight is something which depends on the occupancy.
Okay. But then my question was, can you get branch point from that? Because that.
Okay. Right. Can we get, okay, so I don't know of any way of getting a branch point from this. Remember, here's the it's not a self-energy. It's a something in the green function which diverges, okay? Which gives rise to zeros. I just want to get to this point right here. Yes, that's right. Right. This blue surface right here is the key thing in Mott physics. And this blue surface shrinks or expands depending on where you are in filling. Okay? That is the novelty in this whole Mott problem. And that will only occur over a region where these bands have equal occupancy.
Mm-hmm.
Okay? And as long as you have that, you have a non-trivial green function. Okay. So I know that it's sort of knee-jerk in solid-state physicists' minds that you need branch points to get novel physics. All you need is this. As long as part of the K-space looks like this, you have enough to generate UV-IR mixing.
Okay. So at the end of the day, what you are saying, because we will average on the momentum space, and so you get something very, very non-trivial.
Yes, that is right. That is right. That is absolutely the whole point here. And I know why people didn't do what we did in 1992. Zeros hadn't even been talked about. Mottness really wasn't anything. So there was no reason to suspect that this model had anything that was relevant to any bigger story. So, yeah.
Okay.
I have a question. So you looked at the pairing instability in this HK model, but I'm wondering about magnetic instability. Is it possible to get antiferromagnetism like the Hubbard model, or is that something you lose because of the commutation of the
Yes,
kinetic? And
we absolutely cannot get that.
I see.
Okay, in fact, yeah. I mean, right. There is no antiferromagnetism. And I have always, which is why I emphasize Mottness, early on when David Campbell was still at Illinois, that the problem had nothing to do with antiferromagnetism. The problem had to do with Mottness, and antiferromagnetism was just something to distract people, thinking that they'd accomplished something. So the deep physics is a model which has these blue regions.
I see.
Okay.
Okay, thank you.
Sure.
Any other questions? Okay, so maybe let's thank Professor Phillips one more time.
Thank you. Thank you. This was a pleasure. I hope this format wasn't so strenuous on you. I know this is not perfect, but hopefully we'll survive this whole craziness.
Yes.
John,
What?
we're Skyping or Zooming now. Which?
I like Skype.
I can't hear you.
I prefer Skype.
Louder.
I prefer Skype.
Okay.
Bye.
Okay.